So our first speaker today is Tim Blackmore. He's a Senior Principal Verification Engineer at Infineon Technology. His talk today is on novelty-driven verification, using machine learning to identify novel stimuli and close coverage. As I said, he's a Senior Principal Verification Engineer at Infineon. His research focuses on improving the efficiency of verification of complex IPs, subsystems, and SoC. He's the Global Verification Manager for Infineon's current family of Alrix 3G microcontrollers, and he's located in Bristol. Okay, thank you, Tim. Over to you.
Thanks, Mike. Yeah, so this presentation was given at DVCon last year. So it was joint work with a company called Luminovo. So they're a machine learning startup company, or at least they were when they did this work. And they did some initial experiments for us, and then we replicated those experiments. In particular, that replication was done by Reese. So just to give some background, so what we wanted to do when we started this project was to use machine learning to close coverage more quickly. In particular, when we have no obvious deterministic relationship between a test and the coverage we're aiming to hit. The design we decided to do this on was the radar signal processing unit developed here in Bristol, or we call it the RSPU. And the reasons we decided to use this design should become apparent as we go through the presentation. So just a quick overview of the design. So it's there's a data processing pipeline here. So data is either pushed in from a radar front end or fetched from memory and moved along this data processing pipeline. This pipeline's extremely configurable. It's large and configurable. This is a complex IP, and a test would consist of a configuration of the pipeline and the data to be fed into the pipeline. We've got two types of coverage that we could collect. There's configuration coverage, just to check that we've got a suitable range of configurations and all the interesting configurations that we can think of. And the configuration coverage is naturally determinable straight from the test, straight from the configuration part of the test. So this coverage is pretty easy to hit. We can hit it pretty deterministically. In fact, we do. We actually generate tests to hit all of our configuration coverage. The bigger challenge is hitting this white box coverage. So this is the coverage which looks inside the implementation, looking for corner cases inside the implementation, and this coverage can be very challenging to hit, as we'll see in a while. So there's an important thing you need to know about our test bench, and that's that the test generation is decoupled from the simulation. So we generate a complete test. That test is then stored before it's passed on to a simulation environment. So this is different from a lot of environments whereby a test would be passed to the simulator a transaction at a time, and the test probably wouldn't be stored anywhere. It just exists as a set of constraints in a seed. The reason we introduced this environment was precisely so that we could store a test and avoid random instability problems we were having, which were meaning that we couldn't close our coverage rapidly enough. But it also has many other benefits, and hopefully I get a chance to talk about those in a future DVClub. So one of those potential benefits is that it enables the introduction of a test selector between the generator and the simulator. So the idea here is that you would select the tests that you thought most likely to add to coverage to pass on to the simulator. Okay, so that's all very well, but a couple of obvious questions is why bother doing this? Why not just simulate all the tests you generate? And secondly, if you are going to bother, why use machine learning to select those tests? So we'll answer those questions on the next couple of slides. So the first question, why bother? is based around this 6 months. The answer to that is this 6 months. So, it has historically taken us about 6 months to close coverage to hit all those white box coverage items for the RSPU. During this time, we simulate around 2 million tests. So a large number of tests. We rank the tests and we add any tests that add to new coverage to a ranked regression or a golden regression. And when we do this at the end of the project, we end up with about 3,000 tests, something just over 3,000 tests. So that means we've got a huge amount of redundancy here, 2 million tests down to 3,000. That's some redundancies certainly desirable, but this seems like excessive redundancy to us. So the goal was to reduce that redundancy. Reduce that redundancy by reducing the number of simulations we needed to do. Just one other thing to note is the generation is rapid and the simulation is slow. So really, it's a simulation we want to reduce. If we have tests that we generate that we don't simulate, the cost we pay for that is very small. So that was the motivation for doing it. The second question was why use machine learning. I'll just go into that in a bit of detail here. So first of all, you could try to maybe just use a traditional algorithm. You could maybe write a function that would take a test and predict what coverage it would hit, exactly like we could do for our configuration coverage. But as I said, this function would not be easy to write for the white box functional coverage. There's not really any simple deterministic relationship between our test and our white box functional coverage. So that wasn't a good place to go. Next, we could think of using supervised machine learning, so to train a neural network or something to learn this complex function that would map a test onto coverage. So we'd supply this model with the tests we've simulated to date and the coverage that those tests have achieved, and we'd learn a function that would map those tests onto that coverage. But of course, the problem with this is we have no examples of tests that hits coverage that we haven't hit yet. So that part of the function would not be learnable, and that's exactly the part of the function that we're interested in, the bit that would tell us which tests hit coverage that we haven't hit yet. So supervised machine learning doesn't sound like a good place to go for this. So we next moved on to explore an unsupervised machine learning. And this is typically used to find patterns in input data. So how data clusters, or whether there's anomalous data in the input data. And that made us think. It made other people think as well before us, but it made us think. And we thought, well, maybe anomalous tests are exactly the sort of tests we want. Maybe those are the tests which are most likely to hit new coverage. So we thought we would give it a go. So we tried various test selectors, various unsupervised machine learning models for our test selector. But the one we like most is the autoencoder. And I just briefly describe what an autoencoder is and why we liked it. So an autoencoder is a neural network, is an artificial neural network, and it has an input layer in which you put your feature set in. So in our case, this would be the features in our test. It then compresses that into a middle layer. So this has fewer nodes than the input layer. And then it decompresses it into an output layer. And the output layer tries to reconstruct the input layer. So then you train this autoencoder with lots of examples. And in the training, you try to minimize the loss between these nodes, the input and the output nodes. And this works well, as long as you configure the autoencoder correctly. This works well, and it learns how to reconstruct data well. What it can't do so well is reconstruct data which is very dissimilar to the data it's seen before. And so actually, if you put new data into a trained autoencoder, the loss actually gives you a good measure of novelty. of novelty of that data. So that's what we used. We selected tests with the biggest loss as the most novel tests. So a couple of reasons why we like autoencoders. So they don't rely on any notion of distance on this input space. So we don't have to, for instance, work out whether the Euclidean distance between two tests is actually a sensible thing to be considering. It's all worked out by the autoencoder. The other thing is that autoencoders tend to scale quite well with the size of the data set. So they, for instance, they don't do lots of pairwise comparisons between the input data, which would become computationally very expensive for large data sets. Okay, so we gave it a go. We ran an experiment. So unfortunately, we hadn't saved all the coverage results for all the tests that we'd simulated over the last 6 months of the closing 6 months of the project. And also we didn't really feel like we could spend another 6 months simulating another 2 million tests and collecting coverage on them. But what we did do is spent a whole week and a weekend using 1,000 licenses and compute resource to generate about 82,500 tests, and collected the coverage to generate and simulate about 82,500 tests and collected the coverage on those tests, and we stored that in a database. And then we added the ranked tests from our ranked regression to the database to give us 100% coverage in the database. We then ordered these tests in 2 ways, so we could do a comparison. One ordering of the tests was according to novelty. Was according to novelty. So according to novelty determined by our autoencoder. And so we did an iterative approach here. So after each 1,000 tests, we'd retrain the autoencoder and then find the most novel tests amongst the remaining tests. So even towards the end here, it's worth noting that the autoencoder did the training quickly, even when it was training many tens of thousands of tests. And then we sort of emulated the coverage closure according to this test selection by collecting coverage in the order that the tests were selected. Then we did something similar for a random selection of tests in order to emulate a constrained random approach. And these are the results we got. So as you can see, so this is the results for the random selection. This is the results for the novelty selection to achieve these coverage numbers. And this is the saving in tests and in percentage by using the novelty selection compared with the random selection. And as you can see, this is quite significant. So even at 99.5% coverage, we were getting something like a 60% saving in the number of tests we needed to hit this 99.5% coverage, which we thought was really impressive. I mean, it's worth noting, you know, by the time you get to 99.5% coverage, then typically you're only going to have a handful of, or a few handfuls of items to go after by adding manual constraints into the generation. So we worked out pretty quickly that if we could replicate these results on a real project, then we would save over 1 million simulations and close our coverage 3 months earlier. So we thought this is definitely worth doing, and so we are currently doing it. So I just finished with a few open questions, questions that we don't have answers to. So the first one is novelty a reasonable proxy for coverage? If we could say that novelty was a reasonable proxy for coverage, then we could do things like start to target novelty using machine learning techniques rather than trying to target coverage. And this probably is a far more tractable thing to target, even in terms of trying to generate tests. It's probably easier to try to generate a novel test than a test that will hit coverage that you haven't hit before. The second open question is, does novelty help beyond coverage closure? Actually, is it a good thing in its own right? Will it explore design behavior more quickly? Will it find bugs more quickly? And if the answer to this was yes, then we could really start thinking of novelty-driven verification rather than coverage-driven verification. So we could really start thinking of driving our verification forward by selection of novel tests, and then just close the coverage down at the end. Third open question is, can novelty help us address limitations with coverage-driven verification? So in particular, should novel tests hit coverage? And if they don't, does that suggest that you have a problem in your coverage model? So maybe your coverage model is incomplete, or maybe you've coded up some of your coverage points incorrectly. Okay, so that was the end of the presentation. I've got a couple of questions for myself, but maybe you have some questions for me first.
Yeah, I certainly do. Thanks for the very interesting presentation first, Tim. So these are good open questions. Have you looked at the find more bugs more quickly? Because obviously, you know, we all rely on closing coverage and coverage models as our proxy for finding bugs. But would novelty be finding bugs more quickly, would you say?
Yeah, so don't actually have any results on that. So I mean, an obvious way to go about that would be looking at mutation coverage, I guess. Which approach would cover mutations more rapidly? So then the question would be, do mutations represent bugs accurately? I guess. I mean, the problem with this is always you can't run two projects side by side, or it's very difficult to run two projects side by side and see which one performs better. Yeah, so maybe yeah, looking at mutation coverage would be a way to start to address that question. Yeah.
Okay, there's a couple of questions from participants. If generation of test time is so small, then what is the benefit of use of generated test database? We are using memory storage to store these databases. Not quite sure what the thrust of that question is. Go.
Yeah, I'm not absolutely sure. I mean, the reason is a question about why we why we actually bother to store the tests, or why we store them in a database. I'm not sure. Yeah,
I think that's one. Why do you store them in a database?
Okay. It makes them easy to search for. So we can store them in a way that it makes them easy to find and retrieve quickly. Yeah.
Yeah. Next one's quite an interesting question. What about the limitations in the test generator? Because the ML will only explore within the confines of the test generator. Is that correct?
So it's a test selector, so it will only select amongst generated tests. Yes. So that's true. That's absolutely true. I mean, for us, it's maybe not a massive problem, because the test generation is so quick. So we're not really limited in how many tests we can generate. But certainly it's different to use a machine learning for test generation. So this is yeah. So this is something we are looking at actually using machine learning for test generation, but it's a different class of problem. The test selector is a much simpler approach. So it has a real benefit in that it's simple. For us, this was a really good place to start, partly for two reasons, really, because our test bench structure lent itself to using a test selector, and also because we saw potential for real benefit here. So these are the two main reasons why we started here.
Got it. Yeah. And did you do a comparison with formal methods? I'm not quite sure what type of comparison you do there.
No. No, I'm not sure either. It doesn't occur to me offhand what we would do that though.
Maybe I should screen some of these questions. Sorry. Which features of the test did you use for training the autoencoder? Okay.
So we did quite a lot of feature engineering. So what, for instance, we didn't use the data. We figured the configuration was the more interesting part of the test. So it was the configuration we used, and we even did feature engineering on the configuration. The feature engineering is described in the paper actually in more detail. So it's there to be read. Yeah.
Okay. And did you give a reference to the paper? Is it easy to access that paper?
It's DVCon, and yeah, it's got the same title, and it's in DVCon last year. Yeah.
Okay. Same time. Okay. That's good. Yeah. What type of coverage is it? Functional, line, interface?
It's this white box coverage. It's this white box functional coverage. That's the coverage we were looking at. Yeah, for us that was the tricky coverage. Yeah, we got all the other coverage sort of incidentally along the way whilst we were trying to close this coverage. So that was our focus. Yeah.
Okay. And in terms of the mutation coverage, and you see this as being useful for closing off your mutation coverage more quickly, do you?
Yeah, potentially. Yeah, potentially it could be used for that as well. Yeah.
Okay, because obviously the simulation overhead can be quite high, can't it? Mutation coverage.
Yeah, exactly. So the better the tests you're using, yeah, hopefully the less that overhead. Yeah. So if this could help you select a good set of tests, then it may help there. Yeah.
Okay, that was the last question. So thank you very much, Tim. It's the interesting application of ML to verification. Hopefully, this is a growing area of research for all of us. Well, thank you, Tim. That is a great start. Thank you.
Thanks.